Okay, so last but not least, we've got these hyperbolas. We did ellipses, circles, parabolas, and this is our fourth and final conic section. So we're going to be writing equations of them today, and then in your next video, like I said, we're going to do the graphing for both ellipses and hyperbolas all together. All right, so equations, the equations of hyperbolas. These are the actual hyperbolas over here, which there's quite a lot going on with them. One thing that your graph didn't make super clear is there should be, like these lines right here should be all dotted lines. So really the hyperbola itself is just this graph. Okay, so just this and this. Okay, so that one is considered to be a horizontal. Okay, this is the horizontal one right here. And that is because, see the way that this opens up? It opens up to the left and to the right. So we consider that to be horizontal. And then this one, just this part and this part. Just that part is the hyperbola. The rest of it, the dotted lines, the box, everything like that, just really helps us to guide how to graph that hyperbola, how wide to make it, where to start it, things like that. So this one is the vertical. And that's because it opens up and it opens down. So we've got a whole bunch of features that I want you to look at. We've got the center. So these ones, just like the ellipses, are drawn as if they're centered at the origin. And then we can move them left, right, up, down, just like we did with the ellipses. And then there are two axes that this one has as well. So in the ellipses, we had the major axis and the minor axis. The major was always the larger, the minor was always the smaller. Here we have what we call the transverse and the conjugate axis. Now the transverse, it doesn't matter if it's larger or smaller. The important part is that it's going in the direction where the hyperbola opens. So in the horizontal hyperbola, the transverse is the horizontal axis, and in the vertical hyperbola, the transverse is the vertical axis right here. So it's this distance, and you still find it the same way, like this distance is still 2a, this distance is still 2a, just like in the hyperbolas. And then the conjugate axis is basically the other axis. So in the horizontal hyperbola, it's this vertical axis right here. And this line is still 2b, just like it was with ellipses. And with the vertical hyperbola, the conjugate axis is the horizontal one here. And that line is, again, 2b. So let's set up this one. If you look at these equations, they are incredibly similar to the equation of the ellipse. The only difference is that we've got addition in the ellipses and we have subtraction in the hyperbolas. Okay, so subtraction. Now it is important which order these are in. In these ones with the conjugate, it doesn't matter if A is bigger or if B is bigger. A represents the transverse axis and B represents the conjugate axis with these ones. There's no size difference like there was with the ellipses. All right, so the orientation, this one, since the X is first and then we subtract the Y, that's the marking of a horizontal hyperbola. And this one, when the Y is first and we subtract the X, that is the marking of a vertical hyperbola. All right, so the length of the transverse axis for both of these is the same. Here we're going in a horizontal axis, so you go left and right, A units for the transverse axis. That makes the total length 2A units. And here we go up and down A units, which makes the total length 2A units. And then the conjugate axis, since this is horizontal, the conjugate axis is how far you go up and down. And so you've got a B under here, so that would be B units up, B units down for a total length of 2B. With the vertical hyperbola, the conjugate axis is how far you go horizontally. So B units to the left, B units to the right, again for a total length of 2B. So we still find the vertices and we find the co-vertices the exact same way. All right, so our vertices, you start at 0, 0 with this one. We're assuming that we're starting at 0, 0. And we go A units left and A units right. So your vertices would be plus or minus A, but then 0, because you're not going up or down at all. And then here, we're going A units up and A units down to get to our vertices. So A units up, A units down. So you're not going left or right at all from the center, but you could go up A units or down A units. Then the co-vertices, with this horizontal one, it's B units up, B units down. So you're not going left or right at all, but you could go up or down B units. And finally with the vertical, your co-vertices are to the left and to the right, b units. So you could go left or right, b units, but you're not going up or down at all. Okay, and again, this one we are assuming that it is centered at the origin, just at 0, 0. In our next video, we'll talk about moving it around. And then finally, we've got these asymptotes. So the asymptotes are what set the hyperbolas apart from the ellipses. So these dotted lines right here represent our asymptotes. So we've got 2 dotted lines, and this should be a dotted line. I feel like this figure came out really strange. So that should be a dotted line. These 2 should be dotted lines as well. And these are the asymptotes. So we have dealt with vertical asymptotes and horizontal asymptotes before. This is the first time that we're dealing with diagonal asymptotes. So basically they're really, really important because they show us exactly how wide or how narrow our hyperbola is supposed to be. It really helps us to guide that graph and how the shape looks. So the equations of the asymptote here, for these ones, note we're trying to get to like this point here. So we're going up b units and then over a units. So it's kind of like a slope thing. So going up b over a means the slope would be b over a. Okay, so we have y equals b over a, and that's the slope in front of the x. And then notice this one goes down b units and then over a units. So it looks like we've got either plus or minus b over a. That gives us those 2 different lines. Whereas this one, we go up a units and then to the right b units. Or for the second one, you go down a units and to the right b units. So this asymptote would be, the slope would be a over b or negative a over b times x. Both of them have y-intercepts of 0 because they go right through the origin. All right, so those are our asymptotes. So for these examples and the rest of this video, we're just going to be coming up with the equations for these hyperbolas. So this one, write an equation for a hyperbola with vertices at 0, 2, 0, negative 2, co-vertices at positive 4 and negative 4 with 0. Okay, so we're going to sketch in exactly what this would look like. So our vertices are at 0, 2 and 0, negative 2. And then our co-vertices are at negative 4, 0 and positive 4, 0. All right, so these ones, little different. So with the hyperbolas get sketched. See how it's like now I have these 4 points. It's the same way I had these 4 points right here. So 2 really, really important things when you're sketching it. First of all, you're going to use these points to make this little dotted box like this, and then you put the asymptotes through that dotted box. Okay, so this, you make your little, I'm going to do these in different colors. Okay, so you kind of make this little like dotted box using those points, and then you draw in these dotted lines. So it goes right like through the corner, through the center, and out the other corner like that. All right, so now this one, since our vertices went up and down, that means the hyperbola itself is going to go up and down. So it's going to be a vertical one. So it'll look like that. Okay, so knowing that it's vertical means that we are going to use this formula right here. So we know we start with y squared over something, and then minus x squared over something equals 1. We've got that for sure. So now if you look, the denominator here is a, so that's supposed to be the length of the vertices, from the center to the vertices, and then this is the length from the center to the co-vertices. So here, to our vertices, we're going 2 units up, 2 units down, so this should be 2 squared down in the denominator, which is 4. And then here, we're going 4 units to the right, 4 units to the left, so we should have 4 squared, which is 16. All right, so that is my equation. Just like the ellipses, these will get easier as we practice them more. All right, so let's look at another example. This one, we know it's going to be a horizontal hyperbola. All right, so let's set that up. Horizontal hyperbola is going to be x squared over a squared minus y squared over b squared equals 1. So we've got that for sure. And then you've got asymptotes and vertices. All right, so we should be able to set all of this up. So if we look back at the horizontal asymptotes, so for horizontal, our asymptotes are plus or minus b over a times x. So we know that b over a reduces down to 3. So just based on this right here that we're given. So we know that b over a must reduce down to 3. And then they give us the vertices. Okay, so the vertices are 0 and then 2 root 10 and negative 2 root 10. So let's look at what these vertices are supposed to be. All right, so this is supposed to be, we're supposed to be horizontal. All right, hold on. So our vertices. Those should be, all right, so this must be a vertical hyperbola. I think now that I'm looking in the book, I must have made a typo there. Because if this is a vertical hyperbola, these vertices should have zeros as x's and then numbers as y. So let's just swap these real quick. I'm sorry. Apologize. Need to make a couple of changes. So that would be y, that would be x. And then that would make this a over b, just kind of swapping things around. All right, so let's look back at this. Knowing that it's supposed to be vertical, my apologies, that means a is that 2 root 10 number. All right, so we've got that. So this is supposed to be a. All right, so we know. Here's what we've got so far. We know that a is equal to 2 over root 10. And then we know since 3 is the slope of these lines, this line is supposed to be a over b. All right, so we've got enough information that we can kind of put this all together. So we know for sure that a is 2 root 10, and then we know that a over b reduces down to 3. So we know that 2 root 10 over b reduces down to 3. So we're going to cross multiply. So I'm going to write this as like 3 over 1. So cross multiply here, and we have 3 times b equals cross multiply here, and we've got 2 root 10. All right, so we're going to simplify this down. So divide both sides by 3 just to get that by itself. So that is our value of b. We've got 2 root 10 over 3. All right, so this is going to be a little bit more complicated probably than what you would normally see. But let's put all this together. So we've got y squared over a squared. So we know that this is a. So it is 2 root 10 quantity squared, and then minus x squared over b squared. So this is our value of b. So we have 2 root 10 over 3, and we are going to square that, and then equals 1. So lots of simplification that needs to be happening there. All right, so this, when I square this, I am going to have 2 squared, which is 4, and then times root 10 squared, which would just be 10. So that would reduce down to 40. Minus, all right, and then if I do the exact same thing here, this I've got x squared over, and then if I square all of this, I'm going to have 2 root 10 squared, which I know is 40, and then over 3, which I know must be 9. Okay, so this would be 40 over 9. So not pretty, and you actually are pretty unlikely to actually see things that work out quite like that. Normally they're going to be nice, neat numbers, but that is how we would simplify that down.